Hi again. So we will continue with the likelihood ratio test again, but this time how we deal with the two sample case. As I told you, it's kind of long to solve the questions, but procedure is the same. So we have to find the maximum likelihood under the null hypothesis and maximum likelihood under the whole parameter space of the hypothesis, and then get the ratio. And rejection region will be the cases where the ratio less than lambda 0. Then we try to turn our ratio as a function of one statistic, and based on that we need to find the critical region. So let's start with a normal case and testing the case equality of variances, so you know what we will end up. But let's see how we get the testing procedure, test statistic, and also the distribution of the test statistic. Okay, so two sample case. Okay, so here let's assume that we have two normal distributed samples with mu1 and sigma 1 square, and we assume that we have a random sample of size n1, and we can then calculate the sample mean and sample variance based on this one. So we have also y, let's say, also distributed as normal with parameters mu2 and sigma 2 square. And again, we assume that we have a random sample of size n2, and we have y bar and s2 square. Actually, I wrote x1. We don't need that. Okay, so also we assume that we also assume that these two samples are independent from each other. Okay, so when we consider the whole parameter space without considering the hypothesis, the range of mu1 and mu2 are from a whole real line, and we have sigma 1 square and sigma 2 square both greater than 0. Okay, so this is the actual range, but let's see what's our hypothesis. So here we assume that hypothesis is given as two population variances are equal to each other versus they are not equal. We are using this test also prior to testing the equality of population means. So we have an assumption that sigma 1 square equals sigma 2 square, and also we have a different solution when the sigma 1 square not equal to sigma 2 square. So before handling that test, we have to conduct equality of variances. Okay, so since here we know that x and y random variables are independent, finding the likelihood function will be very easy actually, because we will just multiply two likelihood functions to get the joint likelihood. So our basic likelihood function will be mu1, mu2, sigma 1 square, sigma 2 square, because we are using two sample procedure. So it will be, because of the independence, it will be the multiplication of one likelihood coming from the distribution of x, and the other likelihood coming from the distribution of y. So because of independence, everything is easy. So usually we are making this type of assumptions to make the calculations easier. If this assumption is not satisfied, so then we have to find the joint distribution of x and y, and then the likelihood function of that joint distribution. So everything will be very complicated compared to this one. Okay, so first likelihood, let's equal, so coming from x, so we have a sample of size n1 here, so 2 pi sigma 1 square and 1 over 2 e to the minus summation xi minus mu1 whole square divided by 2 sigma 1 square I here is from 1 to n1. So one likelihood is this, and then the second likelihood 1 over 2 pi sigma 2 square and 2 over 2 this time, and e to the minus summation yi minus mu 2 whole square divided by 2 sigma 2 square, and here I from 1 to n2. So this is our likelihood function. Also, okay, so we have to decide after this. Actually, we have 4 parameters to estimate, both under the null hypothesis and whole space. So we have 8 parameters to estimate. Okay, so when we consider the whole parameter space, basically, so we have all mu1 and mu2 values are between plus minus infinity, and we know that sigma 1 square should be sigma 2 square. Let's say it's just sigma square. Oh, so this is under the null, let's say, sorry, this should be greater than 0. Okay, so we have this, and under the whole whole region, we have the same for mu1 and mu2, and for the sigma values, we know that, actually, let me write it this way. Not equal to sigma 2 square, but they are still positive. Okay. Oh, sorry. This is the previous one was correct. The whole parameter space. Okay, so sigma 1 square greater than 0, sigma 2 square greater than 0. So this is the parameter spaces that we want to maximize our likelihood function under. Okay, so let's consider the first one. So we know that for normal distribution for random variable x, x case, maximum likelihood estimator of mu1 is x bar, right? So you can derive that. If you don't know, you have to derive it. Since we know that, I don't want to derive it. Okay, and the maximum likelihood estimator of sigma 1 square is s1 square. Okay, and here what I mean by s1 square is the case that we have summation xi minus, let me use capital letter, x bar whole square divided by n. Okay, so not a unbiased one. At the end of maximum likelihood procedure, we will get a biased version of the estimate, and under y, mu2 will be y bar, and sigma 2 square will be s2 square. But again, here we assume that it is the biased version 1 to n2. So these are the maximum likelihood estimators under the whole parameter space of the test. Okay, then the maximum likelihood under the whole parameter space of the test, what we will have to do, actually we have to maximize our likelihood function sigma 1 square, sigma 2 square, and where under the whole parameter space, which is satisfied by replacing mu1 by x bar, mu2 by y bar, sigma 1 square by s1 square, sigma 2 square by s2 square. So let's do this replacement. So we have 1 over 2 pi s1 square and 1 over 2 e to the minus summation xi minus x bar whole square divided by 2 s1 square. This is coming from the first one, and do the same thing for y. So we will have s2 square and 2 over 2 e to the minus summation yi minus y bar whole square divided by 2 s2 square. Okay, so let's change the color. Okay, so focus on this part. Okay, so we have summation xi minus x bar whole square divide by 2. Let's write the open form of s1 square. S1 minus x bar square over n, right? So numerator and denominator cancels out and we will have n over 2 only. Okay, so let's focus on this part. And we have summation yi minus y bar whole square divide by 2. Now let's open up, so this should be 2. Okay, summation yi minus y bar whole square divide by n. Again, this one and this one cancels out and we have n over 2. Okay, then our ratio will be okay, so let's combine the things. So we have 1 over 2 pi and 1 plus and 2 over 2. Okay, and we have 1 over s1 square over n1 over 2, 1 over s2 square and 2 over 2. And also we have e to the minus, we have n over 2 term here, n over 2 term here. When we combine it, we will have e to the n, right? Okay, let's see. Okay, so let's do this. So we obtained the denominator part. Okay, so this will be the denominator part. Let's calculate the likelihood function under the whole parameter space. Okay, so not whole parameter space, under the null hypothesis case. So in this case, we need to maximize the likelihood function under sigma 1 square equal to sigma 2 square case. So here minus infinity, mu1, mu2, infinity, and we will assume that sigma 1 square equals sigma 2 square equals to sigma square, which is greater than 0. Okay, so in the calculation, okay, so let's do the things. So we will need to maximize the likelihood function mu1, mu2 and sigma square actually, where are mu1 and mu2 again under the whole space, and also sigma square greater than 0. So let's do this. Actually, you know the MLE of mu1 and mu2, we need MLE of sigma square. Okay, so when we maximize the ln likelihood procedure here, sigma square divided by this one. Okay, so we will have 2 times mu1 over 2 sigma square equated to 0. So we will end up with the MLE as x bar, so it's not changing. And this do the same thing for mu2, sigma square divided by this one. So we will have summation 2 times summation yi minus mu2 over 2 sigma square, okay, equated to 0, and get the MLE as y bar. Okay, so now the other part. So we have L and L, mu1, mu2. Oh, at this point I forgot to write the likelihood function for the case here. Where should I write it? So let me use a different color. And here, okay, so let's try to write this. Okay, so we will have 1 over 2 pi sigma square and 1 plus n2 over 2 and e to the minus summation xi minus mu1 square over 2 sigma square. Let's put a plus sign here, summation yi minus y bar whole square. Oh, not y bar, sorry. Oops. Okay, so this should be mu2. we didn't maximize yet. Oops, why? Okay. Okay, so this is the likelihood function that we want to maximize. And okay, so as you can see, we have the parts under this as okay, so sorry, I forgot to write this. Okay, then we will have let's see, okay, so we will have n1 plus n2 over minus 2 sigma squared, and plus we have summation xi minus mu1 square plus summation yi minus mu2 square divided by 2 sigma to the 4, equate this to 0, and we will end up with sigma square equals summation xi minus mu1 whole square plus summation yi minus mu2 whole square divided by n1 plus n2. After replacing the heads, we will have sigma square equals summation xi minus x bar whole square plus summation yi minus y bar whole square. Here I is from 1 to n1, here I is from 1 to n2 over n1 plus n2. Remember, if you remember, so put this is a pooled sample variance, or we can write this part as okay, so this part can be written as n1 times s1 square, and this part can be written as n2 times s2 square. And then we can write n1 s1 square plus n2 s2 square divided by n1 plus n2. Remember, this is the pooled sample variance. Or we can say that the weighted average of the s1 square and s2 square. Okay, so let's put all these under the likelihood. Okay, then we will have x bar, y bar, and sigma hat square. Okay, sorry. So we have 1 over 2 pi, and now sigma hat square, n1 plus n2 over 2, and e to the minus summation xi minus x bar whole square plus summation yi minus y bar whole square divided by 2 sigma hat square. Again, let's focus on this part. Okay, so summation xi minus x bar whole square plus summation yi minus y bar whole square divided by 2. Let's open up the okay, I realized that I made a mistake in the previous case when I write n, so this should be n1 plus n2 actually, so over 2, so we don't have the same n value, sorry. Okay, so let's open up the MLE. X bar square plus summation yi minus y bar square divided by m1 plus n2. Again, these two cancels out and we have m1 plus n2 over 2. Okay, sorry about that. Okay, then our maximized likelihood function under the null hypothesis is this one. Okay, then let's get the ratio lambda, which is the ratio of the maximized likelihood under the null over the maximized likelihood under the whole space. So we have 1 over 2 pi sigma hat square m1 plus n2 over 2 e to the minus m1 plus n2 over 2 divided by 1 over 2 pi. What was this likelihood? Let's check. Check. Where is it? Oh, okay. So we have this. 2 pi n1 plus n2 over 2, 1 over s1 square n1 over 2, 1 over s2 square n2 over 2, and e to the minus n1 plus n2 over 2. So this n1 and e to the terms cancels out. This 2 pi terms will cancel out, and what we will have here will be okay, so we will have s1 square and 1 over 2. We have s2 square and 2 over 2 divided by sigma hat square and 1 plus n2 over 2. So let's open up the sigma hat square. So we have s1 square and 1 over 2, s2 square and 2 over 2. Sorry. Okay, so what we have here, n1 s1 square plus n2 s2 square divided by m1 plus n2, and we have m1 plus n2 over 2. Okay, so now we have to think. So we have s1, s2 values and the combinations at the end. So let's do this. So we have a power of n1 over 2, we have a power of n2 over 2, and we have the combination here. So let's separate them like this: s1 square divided by n1 s1 square plus n2 s2 square divided by n1 plus n2 over n1 over 2, and do the same thing for the other side. n1 s1 square and 2 s2 square divided by n1 plus n2 and 2 over 2. So now we have, you can see something actually. So we have s1 square here, we have s1 square here, s2 square here, and we have s2 square here, s1 square, s2 square here. So when we, if we, so we try to get one statistic, right? Test statistic here. So how can we do that? Either by dividing s1 square to the denominator, and then write this as s2 square over s1 square, or we can do the same thing here by dividing s2 square s2 square we will get dividing s2 square to both sides, so we will end up with s1 square over s2 square here. Okay, so let's try to find the battery. Sorry. Okay, so let's do this to both sides. Okay, I couldn't find it. Sorry. Okay, so let's do that. So we will have n1 plus n2 the numerator, and we will have okay, n1 plus n2 s2 squared over s1 squared. Okay, so we have n1 over 2, and we have the same here, and n2 plus n1 here, s1 squared over s2 squared, which is this one. Okay, so here, as you can see, we have the same statistic actually. So this one and this one, so it's just the ratio of the other one, inverse of the other one. So let's try to write this term as, so basically you can use one of them. If you want, you can just stick with s2 square over s1 square, and we try to write this in terms of the other one. So let's do that. Or you can use s1 square over s2 square and change the other one, so the result will not be changing. Okay, so when we write lambda, then we will have the constant n1 plus n2, n1 plus n2 over 2, and s2 squared, s1 squared here, n2 over 2, this term, over, we have n1 plus n2, s2 squared, s1 squared, n1 plus n2 over 2. Okay. Okay. Okay, so now we have a statistic which has a function of s1, s2 square over s1 square, so everything is nice now. And then what is our rejection region? Reject h0 if our lambda is less than lambda 0. Okay,